Welcome to the deep dive. You've sent us a stack of urgent security advisories this week, and we're going to distill them instantly.
And one really stood out.
It did. Today, we are focusing on a critical vulnerability in one of the world's most popular NoSQL databases. We're talking about a high-severity flaw in MongoDB that's already been christened MongoBleed.
Yep. Not a name you want to hear.
Our mission is to move past the headlines and extract the crucial, actionable details on CVE 2025-14847. We need to know exactly how this works, why it's being exploited so quickly, and, most importantly, what you need to do right now to protect your data.
And this is an immediate call to action. The urgency here is non-negotiable.
So what makes it so bad?
What makes MongoBleed so catastrophic is that it is an unauthenticated information leak. You don't need a password. You don't even need a legitimate session.
Wow.
An attacker can essentially force the MongoDB server to cough up chunks of sensitive in-memory data, and we have confirmed reports of active exploitation.
Already?
Already, starting right after the public proof of concept dropped.
Okay. Before we get into the technical weeds, let's draw a crucial line for everyone listening, because MongoDB has two flavors, right?
Right. This is important.
If you are using MongoDB Atlas, that's the managed cloud instance, you can take a deep breath. The service provider has automatically handled the upgrades for you.
You're safe there.
But if you are running self-hosted MongoDB instances on-prem, on a VM, in a private cloud, you are the one holding the bag. This discussion is for you.
Let's start with that name, MongoBleed. When security researchers nickname something after HeartBleed,
Oh yeah, I remember that one.
everyone does. It signals a very specific high watermark of risk. The comparison is deliberate because, just like HeartBleed, this vulnerability allows a remote client with zero credentials to extract memory fragments directly from the server process.
That's the terrifying part. So the attacker isn't like guessing a password or injecting a command.
Yeah, nothing like that.
They are physically forcing the server to just dump its secrets.
Precisely. And if we look at the official severity metrics, they confirm the worst. It's a high-severity flaw because the attack complexity is rated as low.
Low complexity, so easy to pull off.
Very easy. Remote exploitation, unauthenticated access, that combination is what security teams dread most. It means this is easily automated and immediately weaponized.
And we know exactly when the game changed. The source material shows a working public exploit was released on December 26, 2025.
Yeah, right after Christmas.
So this wasn't some theoretical threat. The window between disclosure and active attack was, what, hours?
It's virtually non-existent.
Yeah.
Which is why we need to spend time on the technical aha moment right now. For you, the learner, understanding where this sits is key to grasping the danger.
You mean it happens before the system even knows who you are?
Exactly.
Okay, let's unpack that. Where does this pre-authentication flaw live in the MongoDB architecture?
The root cause is centered in MongoDB servers' zlib-based network message decompression logic.
Zlib. That's a super common compression library, isn't it?
Hugely common. It's foundational. MongoDB uses it to compress network traffic between the client and the server to speed things up.
Which makes sense for large data sets.
Of course. But the critical architectural decision here is that the server handles this decompression before it gets to the authentication layer.
It has to, right? It needs to decompress the message to even read it.
Exactly. It has to see if the packet contains a login attempt, a query, or something else.
So that the server accepts a compressed packet, runs it through zlib, and only then does it check if the user is authorized. The flaw must be in that initial step.
It is. The vulnerability occurs when an attacker sends a malformed compressed network packet. It doesn't look right, but the decompression logic still tries to process it.
And instead of just throwing an error and dropping it,
It mishandles it badly.
the source material gets really specific here, down to the file name. Can you zero in on that technical mistake?
I can. The mistake is a classic length handling error found in a file called message-compressor-zlib.cpp. The core issue was that the code was returning the allocated buffer size. So the amount of memory it set aside for the message instead of the actual decompressed data length. Think of it this way. The server reserves a big bucket of memory for the result, say 10 megabytes.
Okay.
The attacker's payload only decompresses to, let's say, 3 megabytes. But because of the flaw, The code reports that the resulting message is still 10 megabytes long.
I see the connection now. So it's like it promised the client 10 feet of rope, only delivered 3 feet of actual rope, but told the client, yep, here's all 10 feet.
Exactly. And the other 7 feet, that's just filled with whatever random data was already sitting in the server's memory.
The stuff that was next to it on the workbench.
That's it. That randomness is what we call uninitialized heap memory.
Let's spend a moment on that phrase, uninitialized heap memory, because for the learner, that sounds abstract, but it's the golden ticket for an attacker. Why is that memory so dangerous?
Well, uninitialized just means the computer hasn't wiped that memory space yet. It's like a digital scratch pad filled with previous notes.
And in a busy database server.
That scratch pad contains high-value fragments, recently handled user credentials, session keys, authentication tokens, query fragments, even chunks of data from previous database operations.
So the server thinks it's sending back a properly decompressed packet.
Right. But because of that wrong length, it unknowingly staples these random sensitive memory fragments to the end of the legitimate data and sends it all straight to the attacker.
All without ever asking for a username or password.
Not once. This is why the MongoBleed comparison is so fitting. It's a targeted, involuntary server memory dump.
That makes the HeartBleed parallel feel less like hype and more like a precise technical description of the risk.
It really is. And given this mechanism, the sheer number of exposed systems becomes deeply alarming.
So let's connect this to the bigger picture. What's the scale of exposure we're looking at?
It's sobering. Census, which scans the public internet, has already identified 87,000 potentially vulnerable MongoDB instances worldwide.
87,000, that's just staggering. And those are just the ones visible from the outside.
Just the publicly exposed ones. 87,000 databases that are essentially ripe for exploitation right now.
But the risk extends beyond internet-facing servers, doesn't it?
It does. We also see startling internal metrics. WizData, which looks inside cloud environments, indicates that 42% of cloud deployments have at least one vulnerable instance of MongoDB.
42%, and that includes internal-only instances.
It does. So even if your database isn't on the public internet, if an attacker gets a foothold in your network,
Through phishing or something else?
yeah, web server breach, anything, they can use MongoBleed to pivot laterally inside your network, dumping credentials and secrets from internal databases just as easily.
And the patch cycle is made exponentially harder by the huge range of affected versions. This isn't just a flaw in the latest server. This logic has been around for years.
For years. It impacts nearly every major release branch. We're talking current deployments, deeply embedded legacy environments, all of it.
Just to give you a sense of the scope, affected versions include 8.2, 8.0, 7.0, 6.0, 5.0, 4.4.
And critically, all the older end-of-life versions like 4.2, 4.0, and 3.6.
So if you're running MongoDB, the odds are pretty high that you're currently vulnerable.
Very high. And this highlights the risk of these foundational libraries, like zlib. This isn't just a MongoDB coding error. It's a logic error tied to a shared dependency.
Which is why we're also seeing this pop up somewhere else.
Right. The same CVE is assigned to an issue affecting the Ubuntu SureSync package.
Wait, rsync, the file sync tool?
The very same. Because rsync, like MongoDB, uses zlib compression. Now, the exploitation details for SureSync aren't confirmed or as severe, but the fact that the same CVE applies to completely different software.
It signals a systemic risk.
It does. It shows this specific type of length handling flaw might be a problem across anything relying on zlib. It's that common dependency issue.
That's a powerful connection. But let's focus on MongoDB for now. Given that exploitation is active, what is the clear, prioritized action plan for self-hosters?
Priority 1 is simple: patching. This has to happen immediately. If you can upgrade, the fix is in versions 8.2.3, 8.0.17, and so on. We'll have a full list. These new versions have the correct logic that prevents the memory leak.
But security teams often face hurdles. Testing, change control. If patching right now is impossible, what's the fast, reliable workaround to slam the door on this?
Priority 2 is mitigation, and it targets the specific attack vector, zlib compression.
So you just turn it off?
You turn it off. Since the vulnerability requires the server to process a malformed zlib packet, you mitigate the risk entirely by disabling zlib compression in your MongoDB config.
And how do you do that?
You explicitly omit zlib from the compression settings, either network message compressors or net.compression.compressors. By removing zlib, the server just stops accepting that specific type of malicious packet.
What are the operational trade-offs, though? Compression is there for a reason performance. Are we looking at a serious speed hit?
That's a critical question. Disabling compression entirely will increase network usage. It could slow down large queries. However, you have safe alternatives.
Oh, good.
If you need to maintain compression, the source material advises switching to Snappy or CD. These compression algorithms are handled separately from the vulnerable zlib logic and are considered safe.
So Snappy and Ziz are okay.
They're fine. The slight performance difference you might see is a tiny price to pay for eliminating an unauthenticated memory leak.
So the immediate emergency playbook is patch. If you can't, remove zlib from the allowed compressors and switch to Snappy or ZZD.
Correct. And beyond that, there are crucial network hygiene measures that are always best practice, but are doubly important now.
Like what?
This attack preys on exposure. You should ensure your MongoDB server is restricted by strict firewall rules. Ideally, it should only be reachable by internal application servers.
Never the public internet.
Never. Any exposed MongoDB instance is a sitting duck for those automated scripts scanning the 87,000 targets we mentioned.
And monitoring. What signs should teams look for in the logs that might indicate an attack?
Look for two things: anomalous pre-authentication connections, especially connections that just drop abruptly, and any unexpected crashes of the MongoDB process.
Attackers testing exploits will often cause crashes.
Right, do, before they perfect the memory leak. So any unusual behavior in the logs around decompression should trigger an immediate high-priority alert.
And finally, we have to reiterate the danger for those on ancient systems. End-of-life MongoDB versions 4.2, 4.0, 3.6, they're not getting a patch for this.
Never. If you are running these, that vulnerability is permanent. The only path forward is an immediate planned migration and upgrade.
Absolutely. The risk compounds with those old systems.
For sure. But MongoBleed is so trivial to exploit that it really forces the issue.
So to quickly summarize this deep dive, MongoBleed CVE-2025-14847 is a critical, unauthenticated memory leak allowing data exfiltration, and it's being actively exploited. If you manage your own MongoDB, patch now. Or at minimum, disable zlib compression and switch to Snappy.
And just to reiterate that core flaw, the danger comes from processing malicious data before the server has verified the client's identity. That faulty length calculation in the pre-authentication logic is what opens the door.
It's the whole ball game.
It is. But let's return to that thought about zlib. This vulnerability stems from a dependency used everywhere in operating systems, web servers, utilities like StirSync. The fact that an architectural flaw, like an incorrect length calculation, could persist in a fundamental library for years. It raises a really important question.
Which is?
Are we truly auditing our foundational dependencies for these low-level logic flaws? What other widely distributed software that relies on zlib might be quietly vulnerable to memory exposure, even if we don't know it yet?
That's a chilling thought.
The security of the application is only as good as the oldest, least scrutinized dependency it relies upon.
Excellent point. That foundational scrutiny is the only thing that saves us from the next HeartBleed or MongoBleed, and that is the critical thought we will leave you with today. Thanks for joining us for the deep dive.